you find, let's say, an article like values, the chances of you finding something else.
Hello, everyone. Okay, so given that it's 10:30 already, I see that you guys were discussing, but I don't want to interrupt you. But I would start by taking questions for Lab 1. So this tutorial was supposed to be for Lab 2 because it's starting next week. But what I can do is, let me first make sure I can mute. Okay, so I will start by taking questions for any questions you would have with regard to Lab 1. Hopefully this wouldn't take too much time, maybe 15 minutes or so, and then we can start going through Lab 2, where I already posted the document on Avenue yesterday. So I will look into the chat, see questions, and then try to answer them. And in the meantime, I will be opening the Lab 2 document in my tablet. Chats, okay. No questions so far?
Sorry, can I ask a question?
Sure, go ahead.
For question 6, the next perfect number is something like 33 million.
Yeah.
So to put that as an input, I think my computer would have to run for like 3 hours.
Sure, that's a perfect question. Thanks. So you don't necessarily have, and this is something that is good to discuss because it's also related to the mentality of discussing test cases or corner cases, right? Can I just ask, if someone not asking the question, can you please mute yourself such that it's easy for others to hear me? So Nicole, so what I was saying is, first of all, the question that you are saying is great. So let me kind of say this for others to make sure they understand. So the point for the perfect numbers is that they are very sparse, which means after, I guess, the 1,000 we are testing, or the 100,000, I don't remember, that the next one is very big, which means you have to run for maybe millions of iterations to be able to get an additional number into the array. This is the question. My answer is, with regard to test cases mentality, you don't have always to change the output. What I mean by this is, test cases are different based on the input, not the output. Two inputs can give you exactly the same output, but this is also something that is important to test. What I mean by this is, the test case you are asked to add not necessarily has to have a different output, right? It would be very fair to do so, but given the case of this question, it's completely okay, and it's a valid test case that you add a test case with a different input, and it might give you something that is you already had before as an output from another test case, right?
Okay,
So
is a 0 a valid test case? Because sometimes it is technically a boundary case.
that's a very important test case, but remember, perfect numbers, you start from 1. So how your question handles 0, it would be a corner case that is very important to test, right? But in Lab 1, a paradigm I took, or a mindset I took, I didn't want to make it an obligation for you to cover all the corner cases. For example, if a user inputs something that is negative while the program only works for positive, or if the user inputs something that is 0 but perfect numbers should start from 1. So I didn't ask you to do that. So you don't have to, but it would be an excellent corner case to check, right?
Okay, thank you.
Thanks. Okay, I'm not sure where did the button for muting everyone go. That's interesting. But let me look into questions. Abhai, for question 3, let's say we have a number like, okay, which is between this and this. Okay, so this question was, I guess, asked last tutorial. how to handle again, the corner or edge grades between two different GPAs, like for example, something as 89.5. As I said in my answer to Nicole's question, I in purpose didn't ask you to kind of have something that is very concrete for the corner cases, because I said maybe it's better to do that later once you develop in your code, because lab 1 is really the first lab, right? Lab 0 is just environment. But given that you're asking about this, a good approach I would do if I'm developing the lab is I will round up, right? If you have something like this, like 89.5, I will do rounding, which means should be 90, and then I will handle this as 90, right? So I would add a couple of lines of code that round the GPA, especially if it's in the edge between two different GPA grades. Good. Laura, I have a test case for 7B with input this, and the output should be 1. On the online compiler, everything also, and should, but autograder. Okay, so Laura, with regard to leading zeros, this is something that I have investigated with someone else during office hours. There are okay, how would I would say this? Leading zeros are problematic if you consider them in the input. Why? Because we take things as int, and to be honest, I'm not sure yet. I didn't come to a conclusion, but my suspicion is that because of the two's complement nature of signed, remember we said ints are by default signed, right? So because of the two's complement nature of signed numbers, those zeros might end up being ones if you are taking the two's complement or involving them in some mathematical operation, so they don't give you the correct result. In order not to confuse you, I would say, don't consider your input having leading zeros for now. So I guess the only requirement that was mentioned in the lab document is with regard to, guys, can I please ask you to mute? Oh, where did the mute button go? That's very interesting. Okay, anyway, so what I was saying is what was asked in the question in the lab document is to make sure if you have something that has zeros on the right, so it's not a leading zero, but if you flip it, it will be a leading zero, then you should print it in the correct format, right? But the question didn't ask you to handle the case where the input itself has a leading zero. When I say leading zero, it's like the mathematical representation of having zeros on the left, right? These are called leading zeros because they have no value. So I would say don't handle this case for now, right? I hope this answers your question. Fardeen, that should output 100 though. No, it should handle it 1 in fact, because if you flip the number, it should be 0, 0, 1. Yeah, but we said you should ignore. It's problematic anyway, so I would say forget about it, Fardeen. Jack, do we have to make a test case for question 5 of lab 1? Question 5 and question 1, I guess, because both don't take no input. You can, as I was saying at the beginning of this tutorial, a test case not necessarily will return something different. In fact, question 1 and 5 don't take any input, which means you will always see the same output. If you add them, they will be redundant, but you can. If you don't want to, especially for these two, you will not be penalized, right? Ahmed, can we have a separate function for question 6? You can add, as I said before, you can add any functions that you see helper as helper functions as you wish, as far as you are developing them yourself. So that's completely okay. Good. Are there any other questions?
Yeah, I had a quick one. It's about the average question.
Yeah.
So I think previously either we discussed it with you or I talked to a TA about this. It was about the average question. Someone already asked in the chat for something like 89.5. Previously it was said that we can just truncate that down to 89.
Yeah, that's also a possibility. No, okay. What I said was only a suggestion. So let me,
okay.
Thanks Arjun for that. So because it has to be clear, I guess. Anything you are not asked very explicit in the lab document to do, you will not be penalized because it will be unfair. So what I'm saying is if you have something like this and someone truncated it or rounded it down, it will still be okay because it doesn't violate any restriction in the lab question, right? If someone rounded it up, good, it's another way. As far as the question didn't restrict you of doing something explicit, right? So both will be correct in this case.
Okay.
What I said was only a suggestion that what happens in real life, right? If you have an 89.5 in an exam and someone subtracts this 0.5 mark from you, you will be angry, right?
Right.
So I'd say usually what instructors and TAs do is like round it up instead, right?
Okay. All
But
right, thanks.
both would be correct for this question, yes. Okay, good. Let me see if there are other questions. Can we have a separate, oh, this is, okay. So guys, you can send your questions here. And if you have no more questions, I can start in Lab2. You're all good with Lab1? Again, Lab1 auto grader, don't worry about it at all. This is something that doesn't by any means affect you either developing or testing your lab. In fact, yesterday we already replenished our quota because it's the beginning of the month. So you will see auto grading start like passing if you make submissions today, but it doesn't really matter. Don't worry about this. Good. The other thing that I mentioned last lecture, and I would like to confirm because question one is the first real lab. Maybe we don't apply this to question 0. Is first of all, I will do my best to make sure you get your lab 0 and lab 1 grade as soon as possible, maybe by end of this week. The second thing is how we are grading the lab. So we have an automated environment where we take all the repos that all the students submitted, download them, and then do initially 2 things. The first one is run all the test cases we have, the ones you developed, the ones we gave you, and the ones that we have internally through an automated way, look into the results. And then the second thing is run this MOSS, M-O-S-S software or code similarity checking tool across all the repos that you developed and repos on GitHub as well to make sure that there is no evidence of severe similarity, right? There will still be some similarities by default because of the nature of the lab. I mean, you are answering the same question. So we are reasonable. So we will not hurt you, for example, if you have an int-x and someone else has another int-x, right? But if everything is identical, this is suspicious, right? And then the third step we would do is whoever is marking the lab as a TA, he will go into those cases, investigate them closely. And something I want you to know, as I said, like even if you get your grade for lab 0, lab 1, over the semester, we might be asking you for a demo or an interview or something that to ask you about how you develop the lab. But we only do this for very rare cases. They can also be random, just to make sure things are fair, right? If you have any question about this, please let me know. But I wanted to make it clear for you to understand what would happen before you get your grade. Okay, good. So let me start for lab 2. So lab 2 document is already on Avenue. So you can start if you wish. So something to know is, as we said before, it's exactly the same environment as lab 0 and lab 1. You will do it exactly the same way. You have the invitation link, you click it, you accept it, and then it will create the repo. You clone the repo in your Eclipse, again, exactly the same way, and then you create the project and start developing your lab. Good. So, but I hope for lab 2, less questions will be about environment and more questions about the lab itself. And this lab is mainly about arrays and functions, because this is what we covered so far. And I would like the labs to be connected to the lectures, right? In the first lab, in the first question, you will be dealing with like an array-based implementation of vectors in math, right? And you will be developing multiple functions that deal with these vectors. The first one is add vectors, as you will see here. Let me draw. Then here, you will be taking 4 inputs. The first 2 are the input vectors or arrays you will be adding. The third one is the result, right? Remember, we said to output arrays from functions, you pass them as an input because they cannot return arrays. So this would be your result that you are adding the vectors to, and size is the size of all the arrays. You assume, in this question, we assume they are all equivalent or equal, right? Good. Very simple question. Just adding 2 vectors and return the result in a third vector. Then I guess I should be able to mute. That's so sorry. Can I ask everyone? Okay, now I got it. Good. Okay, that's good. Then this was the first function about dealing with vectors. The second one is you will be doing a scalar product. So we added 2 vectors. Let's do a scalar product for these 2 vectors. Again, you will take 2 vectors. You will have a result vector as well. You will have their size, and then you will do a scalar product of the 2 inputs, return this to the output. And then the third function is a norm function where simply the norm of a vector in math is defined as the square root of the scalar product of the vector with itself. So what you will do is you will get the scalar product of the vector with itself and then take the square root of this. Clearly, having the scalar product of vector with itself, you can utilize your scalar product function, right? So this is why you are asked in this function to call the scalar product function and then do a square root, because here you need a square root. So you are allowed to use the math library function. Good. And here we make it very explicit. I don't want you to implement a square root function in C for now. Good. And here this gives you some examples of assume you have these 2 vectors as an input, x and y. The sum would be simply taking every element of the first vector, add it to its corresponding element in the other vector, and then it will return to you the first element in the third vector. So if we write this in, let me do this. I guess having some drawing would be good. Okay, so here I would share that. Okay, so if you have these 2 vectors in math, I know that that's very basic math, but if you have this x, which is going of x0, x1, x2, for example, right? And you want, oh, it doesn't write? Okay, so I guess you guys don't see my writing because I don't see it on my laptop. So there is a delay here. Interesting, and this is because of the pen. No. Okay, stop sharing, then reshare. Okay, I'm back, I guess, right? I got disconnected, is that correct? Do you guys like hear me now, right?
Yeah, we see a square bracket and that's it.
Yeah. I got disconnected. It's like, okay. So I will go back, share. Okay, good. So what I was saying is, not this. Huh. Okay. So we have 2 vectors, x and y, and The first one is we add them. So we do a vector add. So how we do a vector add, very simple stuff. You have, assume you have only 3 elements. You guys didn't deal with MATLAB so far, right? Is that correct? So you didn't have any course that deals with MATLAB, I guess. But MATLAB is mainly vector based. So you'll do this thing, you'll do these things heavily in MATLAB. So if you are adding 2 vectors, what happens is you have to take the first element, add it to the corresponding element here, and then put the result in the corresponding index in the output, right? So everything has to match by the same index. So you take it element by element. So it's called element-based operation, and this is called like the vector add, right? So that means, as an example, z0 would be x0 plus y0. One thing that the question assumes to remove any complexity you might have, because there are special cases. What if x and y are not equal in size? How can I handle this, right? You are not required to do this in this question. We assume that all the 3 vectors have the same size, which is passed to the function as the last parameter, which is the end size, right? So you assume that everything is the same. Don't worry about inequality of sizes right now. Good. This is with regard to that. For the scalar product, it's the same thing, because scalar product of matrices or vectors is different than the regular matrix multiplication or vector multiplication. What you would do is, again, you do it an element based. So you would take, in the case of the scalar product or dot, you would say these, usually people for scalar product, they're represented by the dot. And the multiplication is just the normal multiplication. This z0 would be x0 multiplied by y0. x1 would be, z1 would be x1 multiplied by 1. Good. For the norm, what you can do, if you are taking the norm of x, simply the norm of x should be the scalar product of x by x and then the square root of that. So this is the third function. This is the first one, and the scalar, this is the add, and the multiplication or scalar product is the second one. Good. As in lab 1, for every question you are asked to add your test cases as well. Good. Is there any question here? Okay, I guess that's simple enough. So going back to the lab document. For question 2, a little bit adding in complexity. We don't deal with vectors, we deal with matrices. So it's a 2D array. And what we want to do is we want to determine whether whether a matrix is diagonally dominant or not. What is a diagonally dominant matrix? It's simply the matrix that where for each row, you take it row by row, the diagonal element has a value that is larger than the sum of all the other elements, right? So for example, if I take something like 4, 1, 2, is this diagonally dominant? Yes, because here the diagonal element is 4. If you add all other elements, it gives you something less than 4. What if it's 3? Let's say it's something simple. What if it's 0? Then it's not diagonally dominant, right? So you return, so what you return here is you return end. This is 0 or 1, whether it's true or false, based on whether the matrix is diagonally dominant or not. In the case of 0, that's false. Let me ask you a question. What about 3? Is this diagonally dominant? What do you think? No, right? Because the definition is saying very clearly it's strictly larger, right? And if you see the condition here, we don't have equality, right? So it has to be strictly larger. Another thing is, why are we returning int if we are checking something whether it's true or false? Simply because C doesn't have Boolean type, and now we are returning int. This int should be 0 or 1. Good. We are doing this for a square matrix, n by n. Good. So you know that you are taking it should be the n size here should be n2, so it's n2 by n2. You will find n2 defined in the questions.h as in lab 1 and as in lab 0 as well. You will see that I put all the functional prototypes are in the header file, so in questions.h, and n2 is also defined in question.h. Good. So for this, to determine this, because you have to do that, this thing is the absolute value, right? So to ignore the sign, so you can use the absolute function from the math library, right? What does the absolute function do for you? It takes a number and it returns to you the modulus of the or the, it has different names, like the absolute value of this number. So if it's negative, it will be positive. If it's positive, it will be the same value, right?
I have a quick question.
Go ahead, Arjun.
Will the make file for this lab be updated so that the math?
It is already. Yeah, thank you.
Okay, all right.
Thanks.
I just wanted to confirm.
Yeah, sure. Yeah, thanks. Okay. Is there any question about like question 2 here? So we cannot use absolute value or math library in lab 1. Yes, Ishmam, you don't use any. So the lab was clear. And when I was asked this multiple times, I said it in a lean way that you guys don't need to. But the question, like, let me say it very explicit now. The lab document is saying don't use any additional function than printf and scanf. And again, you don't need to, right? Good. Question 3. Thanks. Complete the function in question 3 to see. So just to make sure, Ishmam, if someone already has done this and if you use the math library, that doesn't mean you lose the mark of the whole question, right? But it will be relative to how important is it to implement the logic yourself. So you will use partial grades if you have done this. The same thing applies to the exam. If you are asked not to use something from the math library, most likely I would like you to implement the logic itself that you can use the math library for, and this has partial grade of the question, and you will be losing this one, not the whole grade of the question. A good question, Abigail. No. So as a general rule, don't use printf and scanf at all in all labs, right? And you will see in this lab document, you are not asked to print anything to the screen. So please don't printf anything because it takes time to run stuff, right? And we don't need to. We are doing our testing by the unit testing environment by passing inputs and looking into the outputs. So that's not even needed. Question 3, in which you construct an elements of a square matrix in a diagonal scanner order. Start the left corner, for instance. Okay, that's a good one. So what are we doing here? So we are implementing a function that is called diagonally scan for a matrix. What diagonally scan means in a matrix operation? You take a matrix, let's say it's n by n size, and you transform this into an array representation. This is the first thing. But the array representation has a special format, which is you start from the diagonal here. So it's element 1, you put it your first element, good? And then you scan your elements one by one around the diagonal. So for example, here I would take 5 because this is your diagonal, right? So you'll start scanning 1. After 1 is 5, and then 12, and then 9, and then 13, and then 2, and then 49, right? As you'll see here. Sorry, it's the wrong way. If you do this, you take 1, and then 5, and then 12, and then 9, and then before moving to this, you have to take the diagonal element itself, which is 16, because you are done with, okay, that's my bad. So you do 1, and then 5, and then 12, and then 9, 16, 13, 2, 10, 17, 49, 45, 11, 81, 19, 20, and then 14. So you move, so you can do the diagonal scan in 2 ways, either from left to right or from right to left. Here, you are asked to do it from top left corner, right? So you do it from the left to right, and you move in this direction, right? And then you move in this direction. This is how you, because think about it. If you want to represent a matrix in an array format, there are multiple ways of taking this. One way that happens naturally, if you remember the lecture we discussed in a 2D array, is each row is subsequent, right? So if we talk about the normal representation of a matrix in an array, you will be taking row by row. So you'd say 1, 12, 13, 49, and then you move to the second row, which is 5, 16. So you scan, if I remove this here, the normal representation is to scan rows by rows, right? Another one, you would say, okay, I want to, as if you're transposing the matrix, you scan it column by column. This is another way, right? A third way, which you're asked to do in this question, is to diagonally scan it, which means you are asked to diagonally scan it from the left. So you do something like this. Another thing you can try yourself is, what if I'm diagonally scanning it from the right, right? So you do the opposite side. So it will have 1, 12, 5. So the order would matter, right? Let me see. I see some questions here. Are we going to use? Okay, that's already answered. Yeah. Okay. Is that clear? Like, is the representation clear? Why I would like to do something like that? So what do you think? Why I would like to represent a matrix in such, you might think it's convoluted way? Is this practical? Does like any practical implementation is only for educational purposes? What do you think? It depends on what you want to do with the matrix, right? So remember, I guess I said this in the lecture. Matrix operation is very fundamental in many applications, machine learning applications, image processing, voice recognition, right? So if we take the normal way of dealing with matrices as a 1D thing, which is you take it row by row like that, that means you have your adjacent elements in the row are adjacent in the memory, right? Because this would have, for example, if we start from address 0, this would be address 4. If we're talking about ints here, 8, that means the element next to you is handy, right? It's closer to the memory, which means the cache line you go to bring from the memory will bring probably 1, 12, 13, 49, right? And then getting 5 would take more time. But if you know that you are going to operate on your matrix not in this order, but in a different order. One example would be if you do any image reconstruction or pixelization or pixel filling to improve the quality of your image, you are not dealing with things in a row. You are taking a matrix. I just want you to see the practicality of different programming stuff, right? So you have these pixels in your image, right? For this pixel, what is important is not all the matrices on the same row, right? In fact, what is important is the matrices that are in adjacent to this matrix. So this one, this one, this one, this one, this one, right? So you need your adjacent matrices to be handy to you, right? Not the ones that are in the same row, even if they are very far. So the way you deal with your matrix determines what order it would be better to store in memory, because accessing something that is adjacent to you in the memory takes much less time compared to something that is very far from you in the memory, right? Good. So this is why you will find so many and you'll see this if you take a machine learning course or MATLAB course or DSP or communication course. All the applications, you'll find that the way you store your stuff depends on the way you the way you store your matrix depends on the way that you want to operate on the matrix values. Good. Any question for question 3? Okay, 4. Letter frequency. So remember last lecture on Wednesday, we dealt with strings or character arrays. And I told you that there are so many applications for this, right? One very simple example here we would write is to determine, so we take an array of characters, here we call word, and then we construct what we call the frequency of each letter. So assume I give you this lab document, right, that has 4 pages, and I want you to tell me how many A's are there, how many B's are there, how many C's are there, right? And then you count. So you would write a function that does exactly that. So, but you need to store your value for each letter. for this, we use the frequency array. So as you can see, this is the input to your function that you are going to scan, and this is the output that is going to hold the frequency of each letter. Can someone imagine what would be the size of frequency array? What do we need if we want to count the letters? 26, yes, but 26 is assuming that you are going to deal with small letters and capital letters the same way. So if it's A or A, it has to be counted on the same entry in the array. And this is what we are doing in this question, because if I asked you, one slight alternation for this question is to say, oh, I want you to count the small letters differently from the capital letters. So it's a little bit more detail. To do this, what would be the size of the array I would need? It would be 26 by 2, right? So you would need something like 52, right? So just make sure you understand really the logic of the question, because here we are going to count whether it's A, and this is stated in the question. Frequency 0, for example, is going to hold the count of both A capital and A small. Good? Frequency 1 would be the same thing for B and B small. So we need only 26 elements. Good? So here you are given a hint to make it easy for you, is to, you can do this using the Ascii representation. We know that letters and any character has its own Ascii representation, and the hint is given to you: if a variable x of type character represents a lowercase letter, then the corresponding index in the array equals the integer value of x minus a. What does that mean? So simply, if you look into the Ascii character, you would find the Ascii character table. I might need to switch screen here to also draw something. So if you look into the Ascii table, you would find what if would be the value of a small. Assume this value, I don't remember the value, but let's say it's 36 or 38. I don't remember, but let's say it's, I don't know, a constant c. Good. We don't care about the number for now. Something that is very neat and a trick that is usually used by string manipulation in C is that all the small letters from A to Z are adjacent, right? So if this holds C, this will be C plus 1, this will be C plus 2 until you reach C plus 26, right? So to know, once you know only the Ascii representation or the integer value of small a, you already have handy to you all the Ascii representation or integer representation of all the small letters. And then the A capital starts afterwards. So once you have this, you know. And there are so many tricks that people say, if you have the small representation of a letter, how you transform this to the capital. So for example, if I asked you in one of the exams, do implement a to upper function. In last lecture, we said one of the helper functions in the character C type.h C standard library character manipulation header file is to have a to upper, to lower, is digit, these helper functions, right? So to upper means you take a character here and you return a character as well. You take a small a, you return capital A. So if I asked you to implement this function yourself, how you would implement it? A naive implementation would be take every character, check whether it's A, B, C, D, so you do 26 checks, and then if it's one of them, return the capital one. But that's a very long and not a neat implementation. What would be a good one is again use the relationship between capital letters and small letters in the Ascii table. Good. It would return the same thing. And how? If you do a to upper for an upper letter, it would return the same letter. But what I was trying to say, the main idea is you can use the relationship between different character representations in the Ascii table to do tricks that simplify your implementation of different functions. And here, this lab is one of them, right? So if I go back to the lab question, here, you can simply, as this hint is giving you, you have a variable x that holds a character. the integer value of the small of this character is x minus a because they are adjacent. And the same thing for the capital, it's x minus a capital, right? Because you need this to know where to map your letter into your array. Good. Is there any question here? Good. So let's try to move forward. Question 5, string copy. So what you are asked to do here is you take a source string, a destination, and number of, I guess n is the size of the destination array, right? And then you are asked to copy this into this without using any helper function from the string.h, because string.h has a function that does exactly this. It's called str copy, right? I want you to implement it. How you would implement this: n is the size of the destination, and you have some special cases. I mean, if both are equal size, that's easy. You take it character by character. Can someone remind me, how would I know that I reached the end of the source array? I only have the size of the destination, if n is the size of the destination. How would I reach the null character exactly, and how? Like, you keep searching until, like what we have done in last lecture, until you hit the null character. So you have different possibilities or different scenarios here. If both are equal size, then great, no problem. Take element by element, put it there. If the destination is larger than the source, what you would do? You would copy the source completely to the destination, and then you have to do one extra step, which is terminating your destination by a null character. The third alternative is that the destination is smaller than the source, right? So what you would do in this case, you would have to only pick the number of characters. So assume, for example, I'm copying something like MacMath or university into a destination that has only 4 elements. Good. What you would do? How many characters you would pick from here? What would be the destination correct value? Yes, Karina, perfect. Thank you. It would be Yoni. You wouldn't pick 4. I was waiting for someone to say you would pick Univ, but it would be Yoni without the V, because these are 3 elements, and you need an additional space for the null character, and then you are done, right? So your question should handle these different cases. If both are equal size, if the source is larger, or if the destination is larger. Good. Is there a question? Okay. Question 6. Question 6 and 7 a little bit more involved or complex. And again, it deals with vectors and matrices. And one of its implementations, again, is very common in machine learning, image recognition, and these kind of things. So we define a sparse vector as a vector that has many zeros. Good. And also it's for compression and encoding, by the way. Like if you compress your file using, I don't know, a RAR or tar or any way of compressing files in your system, it does something that's also similar to some extent. Assume I have a vector that has many zeros. This vector might take a lot of space. For example, here I have 1, 2, 3, 4, 5, 6, 7, 8 elements, but I know most of the time it's a sparse vector, so it would have many zeros. So some compression algorithms, either in hardware or in software, what it does is say, I'm going to represent it in a different way. If I know I have so many zeros, it might be more compact to only store the non-zero values and then define their position. So what we would do is we would have 2 different vectors representing this sparse vector. One of them is the value, which holds the non-zero values. Here we have 23, -7, and 48, or -7 and 48. And then we have the position. 23 has the position of 2, -7 has the position of 4, and 48 has the position of 7. Why this might be useful? Because in this very naive example, here we said we have 8 elements in memory, but here both together have only 6. So you saved like 20% of your memory by doing this compact representation of a sparse vector, right? And as I'm telling you, this has so many applications in different things, right? So what you are asked to do, this kind of explaining the context of the question. What you are asked to do, what you are asked is you are asked to write this function called the efficient, where it takes the original source vector, which is the sparse one, this one, and then it's going to write the value and the position, which is the output. So this is input, and the value and the position are the output, which is a different representation here, like these two, right? And then it also takes as an input the size of the vector. Good. Is that clear? So you take a sparse vector, you know its size, so it's passed to you as an input, and you construct the value and position vectors as an output, as a different representation of your vector. Good.
I have a question.
Go ahead, Arjun.
How efficient are we expected to be with this sizing of the value and position in terms of like, well, first, are we given the size of those to begin with? And if not, are we expected to have the size to where it fits exactly the amount of actual values?
Good.
Or can it be the size of the original?
Good, thanks. An excellent question. So the first thing is these are given to you as an input, right? Which means if you are talking about their static sizes, they are already defined. You will find them in the test cases to see, right? Because you are not required in this function to define these arrays anyway, right? So if you're talking about the fixed size or the static size of the array, you don't need to handle this. Now, going a little bit away from the implementation point of view, and it's like in the thinking point of view, what would be the size of these two? Naively, they have to be as big as the original sparse vector, because it might not be sparse at all. This is a valid case, right? Where there are no zeros at all. And that means in this case, your value vector would be exactly the same as source, and your position would be 0, 1, 2, 3, 4 up to the size, correct? So this is what you would do. Practically, but this is beyond this lab, you would be implementing val and position as dynamic size arrays, and we will see this when we talk about dynamically allocated memory and pointers, because you don't want them to go beyond what you need. And each time you increase their size based on the vectors, the values you find in the source, right? But here, because we define them statically, we have to define them as the size of the source, right? Or if I am giving this to you as an input, I would define them such that they hold enough value of whatever non-zero values. But you don't need to care about their size anyway in your question, because this is already handled in the test case. Does this answer your question?
Yeah, that makes sense. And then the other thing is at the bottom of a lot of these explanations, it says write a program to test the two functions. What does that mean? Like, are these
good.
test cases or?
Okay, perfect. That's a good point. So this is another way of saying you need to add a test case, but the word program is a wrong one, because I just used this from my old version of the lab where we didn't have the unified unit testing environment. So students were asked to add a main where they run test cases, but now you only add the test case functions in the test cases.c. I would update this lab document. Thanks for that. I thought I have already removed this, but it might cause some confusions. So yes, only add the test cases. Don't write any programs that has mains or whatever.
Okay, thanks.
Thanks. Good. Reconstruct. So after doing this, you would do the opposite thing, which is assume now I want you to reconstruct the original source if I am giving you the value and the position. So you do the other way around, right? So you would take the value and the position as an input now, which is the compact representation of a sparse vector. And I'm giving you n as a size. And m now is the size of the value and the position. And I want you to construct the source array. Good. But m is the size of the source and n is the size of the input and the input. So instead of giving you the sparse vector, asking you to do the compact representation, I'm giving you the compact representation, asking you to reconstruct the original sparse one. As you can see, like they are the opposite side, they are opposite two blocks. So one way to test this is what? Can you imagine what might be a good way of testing this thing? That is kind of a good way of thinking about to test different pieces of code, especially if they are a little bit involved. I'm doing something that is completely the opposite of the other thing, and the input of one is the output of the other. What I would do, I feed the source in, can you get a few elements in the source and reconstruct matrices? So I would feed the source into the efficient function. The efficient would give me the value and the position representation. Feed this into reconstruct, which is supposed to give me a source, and then compare these two. If they are equivalent, that means the whole process was correct. Does this make sense? Because they are doing exactly the opposite thing. So if you have an input source, if you go through efficient and then reconstruct, what you are expecting to find is the original source, right? So this is a way of testing stuff. It's feedback testing, right? Good. Okay, I guess we are done with time, but let me touch the last question, right? In the last question, it's building on sex and it's saying, now assume I want to add two sparse vectors, but I'm not just adding them simply, I'm adding them using their compact or efficient representation. And it's a little bit complex here, right? Because I take the first vector as value and position, the second vector as value and position, and I want to, and K1 and K2 are the sizes of these inputs, and I want to obtain the added value of this output vector also in the compact representation. Is the requirement clear first, just to make sure you see what I'm meaning? So the final thing is you're adding two vectors as usual, but you're adding them using the compact representation that we discussed earlier. So you'll take the vector not as an array input, you're taking it as two arrays, which is the value and the position, which is the compact representation here, right? So you take two vectors like that. This is one vector. You have another vector similar to it, and I want you to give me the addition of the third in a third vector, right? Can someone say why might this be a little bit more complex than adding just two simple vectors? The very first function we do in the lab, which is taking two arrays as vectors, add them, and then provide the vector. What might be challenging here? Do you have any idea? Remember, we said at the beginning of the lab illustration, to add two vectors, you have to take the first element of the vector, the second element of the first element in the first vector, the first element in the second vector, add them together, put them in the first element of the third vector. But now, the first element here in the value 23, for example, is not the first element here, right? The first element is 0. So if you want to add 23, you have to add it to the corresponding element here that is exactly in position 2, because you have to match the positions, right? The most naive way of doing this is to reconstruct the sparse vector of each of these two efficient representations, and now this gives you the whole vector including the zeros, and then you simply add them. If you do this, you get 0 in question 7 mark, right? Because this is not what you're asking. This is already known, and this you have already implemented in sex. So if you just construct the sparse vector of the inputs and then get the sparse of the output and then transform it to the efficient form, that's 0, right? Because you are asked to develop this in the efficient way. One reason why people do this compression is to make the calculations faster, right? And this is done in hardware, right? So now the challenge you will face is to make sure you match the positions. Don't add anything unless it matches the position, right? So for example, if 23 is at position 2, you have to add the corresponding element in position 2. Just to help you a little bit think on the logic, and then we will conclude by this. How would I know whether this position is a 0 or not? Can someone give a hint? Because now you need to determine whether position 2 in the second vector is a 0 or not a 0. If it's not a 0, then you add it to 23. If it's a 0, then you're just adding 23 to 0. Can someone think of how can I do that? Let me ask an easier question, just to develop the thinking a little bit. A vector, did someone add anything? Let me see. No. So, so simply, if the second vector has a non-zero element in position 2, contains that number, Karina, exactly, correct, thanks. So if the second vector has an element in position 2 that is non-zero, that means your position array of the second vector would have the value of 2, right? If it doesn't have any value of 2, that means position of 2 is 0. So if you check the position here, if it has 2, you take the corresponding element from the value and you add it to 23. If it doesn't have 2, you know that the second vector has a 0 element in the index 2, and then you simply put 23 here in position 2, right? Does this make sense? So position array is key on knowing which elements are 0 and which are not. So this would be the trick that you would start developing the lab through, right? I advise you starting from lab 2 is before even start coding, try to think about the problem and develop a flow chart or know a little bit, a step-by-step representation of what you are going to do. Because if you jump directly to programming, you will be challenged, right? You will be lost with all the details and syntax errors and whatever. So first, the good thing is to develop a flow chart or a pseudocode and then jump into programming after you make your mind about how you would write your implementation. Similar to what I was discussing with you in question 7 here. So we are done with the tutorial for today. We're 6 minutes late already. Sorry for that, but you are free to leave. And if anyone has any question, let me know and I will take that.
Can you explain again the conditions under which we get a 0? Like
yeah,
why you get a 0 for that as well?
Sure. Oh, why you get a 0 for, sorry, what you mean?
Like you said, if you do these things, then you'll get 0 on the lab. Like
okay.
That question. What we're not allowed to do, basically.
Sure. So what I said is in 7, one way of solving this problem, which would be functionally correct, is to say, I have already developed a function that reconstructs the original sparse vector, correct? So I would take the input vectors by value and position, and then reconstruct their original sparse vectors. This will give you vector 1, vector 2, and then simply add them, vector 3. And then afterwards, because I want to return vector 3 in a compact format, I would call the reconstruct function to give me the position 3 and value 3, right? This is a correct implementation, correct? So you are starting from value 1, position 1, do the reconstruct to get vector 1, and then value 2, position 2, get vector 2, add both, simply, just a very simple add like what we do in question 1. This gives you a sparse vector 3. You would utilize your efficient function from question 6 to reconstruct, this would be efficient, not reconstruct. You would utilize your efficient function from question 6 to obtain position 3, value 3, and then return this. But now you did nothing at all for 7, right? What you simply just called,
re-implemented the other functions. And
you called them even, not even email. So you just called them, right? So it's a 4-line implementation. So this is not what this question is for. This question is to see how you can add them in their original format, right? Does this make sense? So you are not allowed to do this, if just to make myself clear. And I guess that the text is already explaining that.
Okay, yeah, because you're defeating the point of the lab. You're just
exactly
copy. Yeah, okay.
Yes,
right,
and also from an implementation point of view, just or the applicability point of view, usually people do these efficient representations to make your arithmetic operations faster or memory storing faster, right? So if you are doing your original operations on the sparse vectors, now you defeated the point of having the compression, right? So it's
right, like
even
you're reverting to the least efficient form and you're implementing
then why originally compress them if you are going to use them anyway in your operations, right?
Right. Okay. Thank you.
Yeah. Welcome. Okay, perfect. So see you all in an hour in the lecture. Then I guess there's something in the chat. Sorry, go ahead. There is a question.
Yeah, just a quick question. Like, I'm late for this tutorial. Are you going to post this on your YouTube?
Yeah. Like all the other tutorials, I'm going to post them. Yeah.
Like today or tomorrow?
Today or tomorrow, hopefully.
Okay. And also, I wonder, have you mentioned at the beginning of the class or not? For the lab one, are we allowed to make a function by ourselves?
Yeah. You feel free to. You don't have to, but if you feel that it's better to define your own function to do something that is
like the lab menu say we are not allowed to use any C library, so I just
correct.
make one.
Yeah. If you write your own function, that's this is different, right? C library, that means the already existing functions in the C standard library. But if you write your own function, that's not C library, right?
Yeah.
Yeah, sure. You are free to implement whatever function. In fact, I encourage you to make your code modular. So if you feel there is a piece of code that is better to have as a function, for example, the swap example we had in our lectures, yeah, make it as a function.
I see. Thank you.
Yeah, thanks, Yanao. Okay, perfect. See you all in an hour then. Bye-bye.